if this will work. Okay, we starting you start by using a little XY table, right? You pick some X's, found the corresponding Y's, plotted those points, and made a curve or a line or whatever. Okay? Now, but students often forget the following simple ideas. If a point works in the equation, then it works on the line or on the graph. Put graph instead of line because they might not be linear equations. And number two, if a point is on the graph, then it works in the equation. Okay? All right, so now some of the problems are going to be really simple. Okay? So you start with this, like it says, determine if the given point is on the graph of the equation. So our point is right here, the 1, 1. So how would I determine if that point is in the equation? Well, what would I do? Just plug it in, right? Don't complicate this, right? Just plug it in. So plug in 1 for X, 1 for Y, and does it give me a true statement? So does it? So we plug in 1 here, minus, and then X is 1, or sorry, equals. What's 1 cubed? 1 minus 2 times the square root of 1, which is 1. So does 1 equal 1 minus 2? No, it does not. All right, now, when talking about graphs, okay, there's a lot of important features that we need to recognize, okay? Obviously, we want to know what shape it is, okay? And by looking at equations, oftentimes we'll be able to tell roughly what its shape should look like, okay? Its end behavior is another one that you talked about in Secondary 3 last year, okay? And there's important points on graphs like intercepts or a vertex, okay, if it's a parabola, a quadratic, okay? Always those kind of things. But intercepts are almost always important, okay? So we're going to talk about getting intercepts right now, okay? And it's actually pretty simple to. So now if you're asked just to find the intercepts, the best way to do is just make a little XY table, okay? Put a 0 in for X, put a 0 in for Y, and then plug each one in and see what your corresponding value is, okay? And really that's all about it. Now plug in a 0 for X will give you which intercepts? The y-intercepts, right? Because if I'm on the y-axis here, okay, my x values are all 0. And the opposite's also true. If I'm on the x-intercept, what are my y values? They're all 0, right? If I'm on the x-axis, my y values are all 0. If I'm on the y-axis, my x values are all 0. Okay, so again, plugging in 0 for x will give you the y-intercepts. And plugging in 0 for y will give you the x-intercepts. Okay. All right, so just quickly in example 3, let's find the intercepts. Okay. So if we want to find the y-intercept, we plug in 0 for x. So we plug in a 0 right there, and what does y equal? Yeah, 2 times 0 is 0, so y is -3. There your y-intercept. That's your y-intercept right there. Okay. And then the opposite's also true. So if I plug in a 0 for y, okay, then I get 0. Graphs. Okay. Now, the first symmetry I want to talk about is symmetry with the y-axis. Okay. So in other words, if I take a graph, fold it in half on my y-axis, right, then the two sides should match up. Okay. That's called y-axis symmetry. It's also called reflective symmetry because the graph reflects itself over the y-axis. Okay. Now, so one example, the most basic example is y equals x squared. Okay, and that graph's a what, by the way? A what? A parabola, right? So it's the simplest of quadratics, simplest of parabolas. Okay. So it's going to look something like that. Man, that is just symmetry in motion right there. That is perfection. Yes, hence math teacher, not art teacher, right? Okay. So now it doesn't matter if you go left or right, you should get the same function value, okay? So it doesn't matter if I plug in 2 or -2 for x, I'm going to get the same y value, correct? If I plug in 4 or -4 for x, or if I plug in 2.7 or -2.7 for x, because I'm squaring them, I'm going to get the exact same y value. That is, that gives us symmetry about the y-axis, okay? All right. So we can generalize this way. If xy is on the graph, then what other point is also on the graph? Negative x and y. Good. Okay. Okay, the second type of symmetry is x-axis symmetry. And again, it's reflective, okay? And the same rules apply, except for instead of the y-axis, the x-axis, right? Fold them in half on the x-axis, it should match up, okay? So again, it should look the same on the top of the x-axis as it does on the bottom of the x-axis, all right? And again, example of that is x equals y squared, okay? So if we go to x equals 4, 1, 2, 3, 4, right here. Okay, what are my y values? So if x is 4, what can y be? 2 and negative 2, correct, right? Because 2 squared is 4, negative 2 squared is 4. So then y is at 2 and negative 2. Okay, if I go to x is 0, y is 0, and there's my graph. Just like that. Oop, I missed. You get it. Okay. So that has x-axis symmetry. Okay. So now we can generalize the idea. If xy is on the graph, then so is x and negative y. Good. Okay. Okay, so symmetry with the x-axis we really don't use too often. How come? Because the graph is not a what? Who said it? Good call, Mr. Tyler. Okay, yeah, exactly. When there's symmetry about the x-axis, the graph is not a function. We like functions in mathematics. Okay, so and that's really why. Okay, because graphs with x-axis symmetry are not functions. Okay. Cool. So that's probably about all you're going to see about x-axis symmetry. Now we're going to talk about origin symmetry here. What I'm going to talk mostly about is y-axis symmetry and origin symmetry. Now, origin symmetry is called rotational because it's not reflecting about an axis, it's rotating about a point, and that point is the origin. Okay? Okay, and again, yeah, it's also called point symmetry there. Okay? So an example of that is y equals x cubed. Okay? So if I were to graph y equals x cubed, hang on, I'm going to blow this up a little bit now. Okay, so if we were to graph y equals x cubed, all right, if x is 0, y is 0, x is 1, y is 1, x is negative 1, y is negative 1. So right now it's linear, but then when we get out to x is 2, then it kind of screws things up. So if x is 2, what's y here? Yeah, it's going to be 8, right? 2, 4, 8. So when x is 2, y is 8. And what about when x is negative 2? Y is negative 8. So our graph is going to look like this. Comes down, looks like that. Okay, now what origin symmetry does is if I basically stick a pin right in the origin and I rotate it 180 degrees, the new graph should look exactly like the old one. Okay? Which in this case it will. Okay? So again, so just if I did a little XY table here for this, negative 2, negative 8, negative 1, 0, 0, 1, 1, 2, and 8. What about 3? What if I did 3? X is 3. What would Y be? 27. What about negative 3? Negative 27. Okay, so if XY is on the graph, then so is negative X, negative Y. Good. Bless you. Okay, so on your homework now, there's going to be some fairly simple problems to start out with. Number one, so if you look at example 4 here, it says plot the point and then the point symmetric with respect to the x-axis, y-axis, and the origin. Okay, so we plot the point 4, 3. 1, 2, 3, right there. There's point A. Okay, so if I want it with respect to the x-axis, what's that new point? Okay, so I'm at, no, I'm sorry, we're using this point here. So we're starting at 4, 3, so with respect to the x, yeah, I got you. So then where's our new point? 4 and -3. Okay, that's your x-axis. If I want the y-axis, then that becomes -4 and 3. And if I want it with the origin, then it becomes -4, -3. Look at you guys. So smart. And there you go. Okay. We won't do point B. It's pretty much the same. All right. So let's find the intercepts of these graphs, and then let's talk about symmetries if they have any. Okay, so part A here. So where are our x-intercepts? X-intercepts are at 2 and -2, right? So the x-intercepts are at 2 and -2. Now, MathXL might ask you to do that. They might ask you to plot them as points. So if I were to put them as points, what would my 2 points be? 2 and 0 and -2 and 0, right? Because when we're on the x-intercept, y is 0. Okay, what's my y-intercept here? Y-intercept is -3. Good. Or if they wanted it as a point, that point is 0, -3. Good. Okay. Now from the appearance here, what kind of symmetry do I have? Y-axis symmetry, correct? Because if I fold on the y-axis, it looks like those are going to match up, and that is true. X-axis symmetry, nope, and origin symmetry, nope. Okay. All right, good. Part B. X-intercept. There's not one, right? That arrowhead flattens out, and it's going to so that x-axis is called a what? If the graph approaches it but never touches it, what's that line called? Asymptote. Good. Good. You don't need to know that right now. That's just, you can impress your friends at parties with words like that.
Big words.
Especially if they're a little drunk or something. Yeah, then it goes over really well. Okay. All right, so what's our y-intercept? Y-intercept is 1. Good. Or as a point, 0, 1. Okay, symmetry. Correct. There is no symmetry as far as that goes. Okay, the 3 we've talked about. Fold it in half on the y-axis, doesn't match up. X-axis doesn't match up. Spin it on the origin, it doesn't match up. Okay, no symmetry. All right. Part C. X-intercepts. At plus and minus 1, right? Okay, y-intercept. None. Origin. Origin. Symmetry. Where did that come from? Symmetry. Is there y-axis symmetry?
Yeah.
Absolutely. Is there x-axis symmetry?
Yes.
Absolutely. Is there origin symmetry?
Yes.
Absolutely. It has all 3. Okay? That is a rare occurrence, but it does have all 3 symmetries. Okay. All right, part D. X-intercepts. Okay, we're at 0. Where else? Then plus and minus 4. Okay. Y-intercept. Yeah, and there's something, and if you think about it, it makes sense. If there's an x-intercept at 0, there has to be a y-intercept at 0, right? Because that's the origin. Okay, symmetry. Y-axis, no. X-axis, no. Origin, yes. So this has origin symmetry. Running down the home stretch of this one. All right, so pretty simple stuff here. Draw the completed graph and label 2 points if the graph has the type of symmetry indicated. So part A has symmetry with the y-axis. Okay. So where would another point be? -2 and 2. All right, it'd be right here. And then you'd also have 0, 4, and 0, 0 on those. Man. Oh, to have my artistic skills. I know you're all jealous. Okay. Okay, so part B now. Okay, we want symmetry with the origin. Okay, so if you need to, look back at your notes on origin symmetry. So if x, y is on the graph, then what else is? Negative x, negative y. Okay? So if I have 0, 4, what's another point on my graph? 0, negative 4. If I have 2, 2 on my graph, what else do I have? Negative 2, negative 2. And if I have 0, 0, I also have 0, 0. So that one looks like that. All right, we okay? Questions so far? Good? Okay. All right, so let's kind of summarize here. So to test for symmetry, here's what we do. If you want to test for symmetry with the y-axis, replace all the x's with negative x and then simplify it. Okay? If we get the exact same equation, then it has y-axis symmetry. And it's also called an even function, by the way. Okay. If you want to test for x-axis symmetry, replace each y with negative y and simplify it. If you get the exact same equation, it has x-axis symmetry. If you want to determine origin symmetry, okay, replace each x with negative x and each y with negative y and simplify. If we get the exact same equation, then it has symmetry with the origin. Okay? And this is and this test is for if we have just equations, right? And no graphs. Graphs is pretty simple. Just like we showed up there. Okay, but equations are a whole different animal. And again, a little note, if none of those work, then it has no symmetry. All right, so for the following now, we're going to list the intercepts and test for symmetry. Okay. So y squared equals x plus 9. So let's talk intercepts first. Okay, so if I want to do my y-intercept, what do? If I want to find my y-intercept, I make x 0, correct? Okay. So if x is 0, what is y? Plus and minus 3, right? There's our y-intercepts right there. Okay, what about x-intercept? So x-intercept, I make y 0, and I get x is negative 9. Okay? All right, now let's test for symmetry. So let's test for y-axis symmetry. So again, for y-axis, I plug in negative x for x and simplify. If I plug in negative x there, do I get the exact same equation? If I plug in negative x for x. No, I don't, do I? So there's no y-axis symmetry. Okay, let's go x-axis symmetry. So if I plug in negative y for y, do I get the exact same equation? I do, because negative y squared is y squared. So it has x-axis symmetry. Now what about origin symmetry? If I plug in negative y for y, negative x for x, do I get the exact same equation? I don't. So the origin is a no. Okay. That's how we do these problems. All right, 57. X-intercept. And 0, right? What about my y-intercept? Same thing. So my x and y intercepts are both at 0. Okay, let's check symmetry now. Do I have y-axis symmetry? Plug in negative x for x. Let's see, so I get y equals the cube root of negative x. Is that the same as the original? It's not, so I don't have y-axis symmetry. What about x-axis symmetry? X-axis, there's still no, right? I plug that in. I plug in negative y equals the cube root of x. That's not the same. Okay, what about origin symmetry? What about origin symmetry? Yeah. We're going to have origin symmetry, and let me show you why. So we get negative y equals the cube root of negative x. Now, the cube root of negative x is the same as negative cube root x. So if I have negative cube root x equals negative y, I can cancel my negatives, and I have y equals the cube root of x. That is the same, sports fans, so we do have origin symmetry. Okay, and just FYI, your cube root function looks, well, I really have room. I know, love technology, but there we go. Tree. Okay, so we're not worried about intercepts here. So plug in x with negative x. Okay, are we going to get the exact same equation? We're not, are we? So we get y. Oops. So we would get y equals negative x squared, which is x squared, plus 9 all over negative 3x. So not the same, so there's no y-axis symmetry. What about x-axis symmetry? So plug in y for negative y? No, that's gonna. Okay. What about origin symmetry? Let's see. So we get negative y equals negative x squared plus 9 over 3 times negative x. So what does that give us? Negative y equals x squared plus 9 over negative 3x. I can cancel those out. Same, same? Same, same. So it does have origin symmetry. All right, x-axis symmetry. So I plug in y for negative y. That's not going to work. Y-axis symmetry. Is that going to work? Let's see. So I get negative x to the 5th over negative x cubed plus 1. Now these, okay, hold on here. I can't just cancel these two negatives out. Why? Because of that right there. So if I change those two, I got to change that one to a minus. So is there y-axis symmetry? No. Close, but no cigar. Origin symmetry. Let's see. Negative y equals negative x to the 5th over negative, oh gosh, come on, negative x cubed plus 1. Okay, so if I change all my signs, do I get the same equation? I don't, do I? Okay, that's kind of screwed everything up. Because what that plus 1 does is going to shift the whole graph up 1, so it screws up all sorts of symmetry there. Okay.